Dear students, Assalamu alaikum. Welcome to your fifth experiment for your DLD lab, and its title is Implementation of a Full Adder without using NAND gates. So this time it's going to be a bit easier for you, but however the concept that you will study in your full adder is slightly different from that of half adder, because it involves detailed derivation from a full adder truth table. So the basic process in designing a full adder is exactly the same, because since it is a design problem, so the steps that you will follow will be exactly the same as that of a half adder, but however the implementation will be slightly more complex. So let's see the ICs you will be requiring are 7408, most probably 7404 and 7432. And to understand a full adder, it is basically an upgraded version of a half adder, and we will see that how it is related to a half adder in my derivation process. And it adds three bits of inputs instead of two, because in your half adder case you have studied that you added 2 bits of inputs to get 2 outputs, sum and carry. But however in this case it is called a full adder because it involves the addition of 3 inputs. And also it is the basic building block or basic foundation unit to build all types of or all sizes of adders involved in the arithmetic logical design. And the inputs are called obviously augend and addend, and the outputs are sum and carry. And here we will write down its truth table, and after that we will derive its equations. So let's move to our basic understanding. Now, as I said, that in a design problem we need to design a truth table, and after that we derive the relevant Boolean expressions, and then we draw the circuit based on those Boolean expressions. So let's first draw its truth table, and its truth table involves 3 inputs A, B and C and carry N, right? And it has 2 outputs. Just in the case of a traditional adder has always 2 outputs, sum and carry, right? We can have various sets of sizes of sums and carries, but however the outputs are of 2 types, sum and carry. Now since we have 3 inputs, so we will have 8 combinations of the inputs, that is 0 0 0 0 0 1 0 1 0 0 1 1 1 0 0 1 0 1 right, it's 1 1 0 and 1 1 1. So what should be the output? In the first case we have 0 plus 0 plus 0. In this case obviously sum will be 0 and carry will be 0. And in the second case we have 0 plus 0 plus 1. In this case this bit is the carry out, and this bit is the sum. So in this case we have 0 plus 0 plus 1, we get 1, and there is nothing to be carried, so our most significant bit will remain 0. So our carry remains 0, 1 and 0. Similar in this case, sum becomes 1 and carry remains 0. 0 plus 1 plus 0, again 1 and 0. Right? In the third case the situation changes a bit. We have 0, 1 and 1. In this case 0 plus 1 we get 1, and then again we add 1 plus 1 and we get 1 0. Why? Because 1 0 is equivalent to 2 in decimals. So we can say that 0 plus 1 gives 2 in decimal, and we represent 2 in binary as 1 0. So in this case our sum bit remains 0 and our carry bit becomes 1. 0 and 1. Now again this is the case where we have sum as 1 and carry as 0. In this case again we have two sets of in 1s and 1 0, so we get sum as 0 and carry as 1. And in this again sum is 0 and carry is 1. Now this time the third case, the last case is a bit different. 1 1 and 1. We get 1 plus 1 1. Again 1 plus 1 becomes 1 plus 1 becomes 2, and 2 plus 1 becomes 3. The binary of 3 is actually 1 1. So my sum is 1 and carry is 1. So this is in the last case, this is the only case in which we have both sum and carry as 1. Now if I try to derive the Boolean expressions out of these outputs, sum and carry, we first need to know that since we have two outputs, sum and carry, so this means that we will have two sets of equations. The first equation is for sum, right? And we will note down that on which locations we get 1. This, and this. So there are two methods of deriving the Boolean expressions. Either we can draw a K-map and try to simplify the equation using the K-maps, or we can simply utilize the simplest derivation method, in which we note down the ones present in any output and then we write the corresponding input variables. So in the first case I'm going to utilize both the methods for you to help for you to understand this both of these processes. So first process is that I'm going to utilize represent the variables, input variables, and in accordance with the ones at the output. So for the case of sum, we have 1 in the second location, in which we have a as 0, b as 0, and c in as 1. So what does this mean? That we will have a complement b complement dot c, and the next case is we get the second one here, where we can write down as a. The zeros are represented as a complement and ones are represented as it is. A becomes complement, B becomes as it is, and Cn becomes complement, right? The third case is here. We have I think this one. Right, we have a as it is dot b complement dot c in complement, plus the last case where we have a, b, and c. Now if we try to simplify this equation, what do we get according to Boolean algebra? If I try to the first not the first, the second, now this one, a complement, right? If I try to yes, if I take Cn as common, C in complement is common in both of the second term, This is the first term, this is the second term, this is the third term, and this is the fourth term. If I try to take Cn complement as common between these two terms, term number 2 and term number 3, I get inside the brackets a complement b plus ab complement plus, and I try to take out c as common in the terms 1 and term 4, and I get Cn, this is Cn, and the terms remaining inside the bracket will be a complement b complement plus ab, right? Now if I try to replace let's say a complement, if I'm trying to replace these terms a complement b plus ab complement with another variable x, let's say, and similarly I can say that a complement b complement plus ab. Now as I know that this is actually representing an XOR gate, because for XOR gate the equation was pretty much similar, that I had the complement of the first variable dot the second variable plus the first variable dot the complement of the second variable. This is equivalent to an XOR gates equation. And similarly I know that the second equation is an equation of XNOR, and I also know that both XOR and XNOR are complements of each other. So they are both complements of each other, so I can write down here that since I am replacing this whole equation with x, so I can replace whole of this equation with x complement, right? This is we can represent the complement like this or this. Both are two ways of representing the same complement term. So let's try to put both of these variables in the original equation. This was my original equation. That is equal to Cn dot x plus Cn complement dot x plus Cn dot x complement, right? So I can see that this is actually representing this equation, this whole equation is actually representing another XOR gate, because according to my XOR we should have the complement of the first variable dot the second variable plus the first variable dot this complement of the second variable, right? If I try to use the same bar to represent the complement term, right? So if I try to write it in this way, Cn XOR x, right? I am actually replacing this whole equation by a single XOR gate, because according to my theory any XOR gate that is available in your XOR IC 7486 IC, it has 1 2 3, the first gate present here, it has A, B as inputs and outputs as A complement dot B plus A dot B complement. So my assumption is that this first gate is actually representing this whole equation. It is performing this whole equation, and I can replace this whole equation by a single operation. This symbol is actually representing the operation of XOR between Cn and x, right? Now if I try to rewrite the original value of x, what was the original value of x? X's original value was this one, A complement B plus AB complement. This is equal to Cn plus XOR A complement B plus AB complement, and I can replace this whole equation again with an XOR gate between A and B. So this will be equal to Cn XOR A XOR B, and I can, if I try to remove these parentheses, it will work the same way. This is equal to Cn XOR A and XOR B. So this is actually my equation for sum. That if I try to take an XOR between A, B and Cn, so how will it work in this IC? That if we try to I will come back to the IC part later. First let's try to derive the equation for carry. Let's use another color for that equation 2 for carry, or I can say carry out. This is equal to, now from this truth table, let's see, the first one appears here. It has A complement A, B and Cn, and the second one appears here. It has A, B complement and Cn. A, B complement and Cn. A complement B Cn plus, let's try to write it down in a more neat way. This will be A complement this is equal to A complement dot B dot Cn. This is the first term. The second term is A dot B complement dot Cn dot Cn, right? And the third one appears here. It has A, B and C complement, and last will be A, B and C. A, B and C complement, Cn complement plus A, B and C. Now let's see that how we can simplify this equation. If I try to take Cn right, now how should we simplify these equations? If we try to take A, B common between both of these terms, A, B, Cn complement plus Cn, right? And next term will be, if I try to take Cn common between both of these terms, Cn, and inside the bracket we will get A complement B plus A B complement, right? So we can see that this is an XOR gate. So, and anything ORed with its complement, Cn complement plus Cn, anything ORed, if I say A plus A complement, we get 1. So anything ORed with its complement, we get 1. So with this whole term can be replaced by 1, A, B plus Cn dot, and I can replace this whole equation by a single XOR gate. There can be other ways as well to simplify these equations, and you can choose any of these. So I can see that A XOR B, this is also happening here in the sum equation. A XOR B is happening here, and if we try to implement the second half of this equation first, and then we take the XOR of the resultant with C in, then we can simply reduce a wire in my final equation. So let's try to make a circuit using, this is the equation for carry out, and this was the equation for sum. So the first equation can be represented like this. We have A, B and C in. We have three sets of inputs, and between the first A and B we are performing XOR operation. So we are getting A XOR B, and after that we take an XOR between A XOR B. So at the output we are getting A XOR B XOR C in. This is equivalent to, this is exactly the same thing that we needed. This is, if we rearrange the variables in this equation, then it doesn't make any difference at the output will remain the same. So this is equivalent to sum. So by simply putting on two XOR gates we are getting the sum, and we can put this wire in an LED to observe the value of sum from the truth table. Now to implement the carry part, what do we need? We need A XOR B dot C in plus A dot B. So we should have A XOR B, that is already been performed here. For the carry part I am changing the color of the wire. This is A XOR B, and I want to dot it with C in using an AND gate obviously, and I will get A XOR B dot C in. Now after that I want to OR this with A dot B. So first I need to get A dot B. This is A dot B, and after that I'm going to OR both of these. And what am I getting at the output? I'm getting carry out, and this should be equivalent to, this was A dot B, and my carry out should be equal to A XOR B dot C in plus A dot B. Now as I said earlier, I can put this to another LED, LED2, and I can observe the behavior of both sum, this was the sum and this was the carry, and I can observe both the behavior of the sum and the carry according to my truth table. But before that, as I was explaining that you can also utilize the method of a K-map to simplify both of these equations. What were those equations initially? Let's try to sort original equations first. The original equations, or we can simply utilize the truth table of a full adder. Let's try to rewrite those let's try to rewrite that to table A, B and C in, and output is sum carry 0 0 0 0 0 1 0 1 0 0 1 1 1 0 0 1 0 1 1 1 0 1 1 1, and output should be 0 1 0 0 1 0 and 0 1 1 0 0 1 0 1 and 1 1. So let's try to put these equations in the form of a K-map. We are going to get two K-maps for both sum and carry. The first K-map should be for sum. We have 3 inputs, so we will have 8 boxes, A, B and C in, right? And for A we have 2 possible combinations, 0 and 1. For B and C in we should have 0 0 0 1 1 1 and 1 0, right? And let's try to fill those ones. We have 1 1 1 1. Since it has no ordered pairs, so my sum's equation will be exactly the same as I got without using the K-maps. So sum will make no difference. So let's move on to the carry equation. A, B, C in. This is for carry. And 0 1 1 0 0 0 1 1 1 and 1 0, right? And I should have 0 0 0 1 and 0 1 1 1. So in this case the equation can be a bit different, because in this case I can see that there are some ordered pairs here. First is this, second is this, and third is this. So for carry we can have an equation, we can have 3 sets of terms. The first ordered pair is this one. Let's suppose it is this one. In this case A is changing, so we are ignoring A and we are using B dot C in, plus the second ordered pair is this one. In this case A is same, so we are using A dot C in because B is changing. And in the last case we have this last third ordered pair, and it has A dot B. So this could be another carry equation that you can try to implement in this. But however, in this circuit I can see that we are requiring 2 XOR gates and 2 AND gates and 1 OR gate to implement this full adder. But however, if I try to utilize this equation for carry, to implement this equation for carry, both of the outputs will be exactly the same. In Boolean algebra, the beauty of this Boolean algebra is that we can actually get a lot of different ways to implement a single circuit and still expect that the output of all of these circuits will be exactly the same. So in this case, this equation of the carry and the other equation of the carry both will have the same output. So we can have you have the advantage to choose that which equation you wish to implement. But in this case we are not actually choosing the carry in carry out this equation, because it involves at least 3 AND gates, because it has 1 2 3 dot operations, 3 AND gates and 2 OR gates, right? So this is involving a total of 5 gates. But however, in this carry operation we are using only how many gates? 1 2 and 3 gates. this is 1, 2 and 3 gates, they are fixed for calculating or computing your carry out. So this means that this equation that you implemented for carry, this is a more optimized version. So to implement this circuit using these 3 gates for carry, you are actually saving at least 2 gates. So I think that either you can, there's an open opportunity for you that you can also utilize the other equation to implement the carry, but however I will suggest that you should uh, keep on the habit of utilizing the minimum number of gates and minimum number of wires to implement any circuit. That will sharpen your optimized approach for any circuit. So for this case you will require how many ICs? You will require at an IC of 7486 for XOR and 7408 for AND and 7432 for OR. Apart from these, there is no other IC required to implement the circuit. Not even an NOT gate is required. If you simply implement this simplified version of your overall complex equations, because if you try to implement these original equations, that will be quite hectic and fruitless for you, because you will be requiring so many gates to implement this equation and this equation for carry and sum. So you will that will not be feasible for you neither it is fruitful. Since you have an open opportunity that you can utilize any kind of gates instead of NAND gates to implement this circuit, then this is the best way, that you simply simplify your equation and then try to implement that simplified version on multisim. You will be requiring the same tool, multisim, to implement the circuit. So let's go back to our week's tasks. First you will write down the derived equations for sum and carry, and after that the task is that you will derive the Boolean expressions relevant to a full adder, just like I told you, and draw a logic diagram for full adder using AND, or NOT, or any other relevant gates. Obviously you will be requiring XOR gate in this as well, and implement its circuit diagram using relevant gates only on multisim, and observe and verify the truth table of full adder from multisim. And I hope that this lab is going to be pretty easy for you. So I will discuss the next lab in your subsequent lecture. Allah Hafiz.